right, welcome to lesson 6.6. Before we get into it here, just a little, like usual, kind of overview where we're at, weekly update or whatever. This ends up being our last lesson of chapter 6. So I know we kind of 6.2 and 3, and then 6.5 and 6. So it's a abbreviated chapter. Obviously, we're kind of bare bones in it here, and just making sure that really you're exposed to these different skills and concepts, and that's kind of all it is. So we're just plugging away. Make sure you're finding time to like legitimately do them. You know, do the assignments, watch notes. I don't ask for much of your time during the week. Maybe hopefully keep it under 45 minutes for the video, and maybe another 30 to actually do the assignment well and understand what's going on. So we'll just kind of keep with that schedule. It's again, like I said a second ago, it's the whole idea here is mainly just exposing you to different concepts that you'll see going forward and learning some new skills. So as far as Infinite Campus, it's always for me a battle to keep that updated. So it's let me know if you resubmit something. It's hard for me to tell sometimes on Google Classroom. I don't really have a way of getting a notification that so and so did corrections or submitted something that was missing or that was late. So let me know. Say, hey, just so you know, Mr. Crow, I submitted that 6.5 or 6.5, 6.4 worksheet that I was missing. I guess we can do a 6.4, but you know what I'm saying. So let me know if you submit something late or make corrections, so I can get you points on Infinite Campus. So I'm working on getting those quizzes in there and all that stuff. This will be how it'll go till the end here. So I think that's it. Let's kind of get into the lesson. It's a good lesson. I like 6.6. There's no word problems. There's nothing weird. It's going to rely on our equation solving skills, which is good. I think a lot of us are comfortable solving equations, but also some of the new stuff. So that's what I meant. I said go back. You might have to watch. A week in between lessons here is tough. I understand that as well. That what did we do last week? You know, you're thinking to yourself. So make sure if there is something, you don't just skip it or just whatever, like go back and just watch a 5-minute clip of the previous lesson. Oh yeah, that's right. That's what we were doing last lesson, because I'll reference it here as we're doing the notes. So let's do it. There's basically two types. We'll start with exponential, solving exponential equation. You can see a couple different examples. It's just like always, they start kind of easy and get tougher. And then solve log equation, same thing. There's some easy ones, and then they'll get a little bit tougher. So I'll do what I've done with the previous ones and try to section it off and let you know in the homework, here's what we got going on. And so let's do it. I think we're muted. We're ready to roll. Here we go. So basically solving an exponential equation. First off, how do I know it's an exponential equation? We've got an unknown. So we've got an unknown x or variable in the exponent. So up until now, I don't think we've really ever solved anything like that. We did a little bit actually at the end of last lesson. So right off the bat here, I'm already referencing last lesson. Stuff like this, where it was 6 to the whatever power equals 20. And it was how do we fix that? And it actually kind of started with log base 6 of 20 equals x. That's kind of how we would start. So just referencing or what we did, connecting it to stuff from last lesson. We started with problems like this. Log base 6 of 20 equals what? What is that value? It was literally the last thing we did, the change of base formula. But remember, what does that mean? It means this. So we turn this into this. So we could answer that question using our change of base formula, log of 20 over log of 6, right? Change of base, I switch it to a base 10. Now I could use my calculator to figure that out. So we have actually done a little bit of kind of solving some like that, and there might be situations where you could kind of reverse this to this to this. We'll look at some other methods here, maybe easier. I don't know. I'll leave it up to you. But basically, I've this statement here that 3 to some power is equal to 3 to the 5th power. Well, what has to be true? This power has to equal this power, right? There's no other way that this statement could be true unless these powers were equal. So we're looking at kind of an easy one here. I mean, that would obviously be very simple. X equals 5. Even this here, I call it example 0 because you got the same base. 3 to some power is equal to 3 to some power. Okay, what has to be true about those some powers? They have to be the same. They literally have to be exactly the same. Otherwise, this could not be an equation. So here's one you end up with a pretty, hopefully most of us would agree, a very, I'll do it in steps here. I've subtracted an x from both sides. We'll add a 1 to both sides and divide by 3. But I was saying, hopefully most of us would agree that that's a very doable equation. That's one that's not going to strain us too much. You could check it. I mean, even just offhand here, 3 to the 2 plus 5 is 7. You don't even need to know what it is. 3 to the 7th power, and then 4 times 2 is 8 minus 1 equals 3 to the 7th power. So that's, yeah, that's not a bad equation to solve. Set equal your exponents. Okay. I think leveling up here a little bit, what makes this one different, example 1, would be something along the lines, well, I guess, I mean, right here, I can see that the bases are different. Well, we looked at one that it was 3 and 3, that was easy. What happens when it's 64 and 16? And I see these numbers and I'm kind of like, there's a connection here, 16, 32, 32. Can I rewrite this 16 with a different base? So let's start with this one, and we'll come to this one because I think I see this one a little bit easier as far as it jumps out at me a little bit better. So step 1, or easier, so that like step 1 would be like, if they're not the same base, see if we can get the same base. Okay. So I end up with, you know, I think 16, that's the same thing as 4 squared. Okay, I've got 4 to the 2nd power to the x plus 1 still. So I still got to be a little bit careful here, keeping track of everything. I've just rewritten basically 16, 4 squared is 16. We all know that. Now, keeping that in mind, that we want to have the same base, well, this one I need to hopefully be able to write as a base 4. So 4 to the 3rd power, 4 times 4 times 4, is the same value, or has the same value as 64. Again, we're still taking it to the x power. So just keep track of that. Have a step where you just write them out here. Get your base for, 4 to the 3rd power. You can check it on the calculator, sure. Maybe that's not one that stands out to you right away. But okay, so now we've got the same base. A little bit of simplifying here. So I've got 4 to the 2nd to the x plus 1. Going back, chapter 5, how do I handle two exponents here, something like this, a power to a power? Well, I multiply my exponents. So the left side actually now ends up simplifying kind of nice, just 4 to the 3x. And then just be careful here. We still want to multiply just like we did a second ago, but I want to make sure that I'm distributing here. Okay, so 4 to the 2x plus 2. Just it's as easy as that, forgetting that 1 and sending them 2x plus 1. It's actually 2x plus 2, makes all the difference. So we kind of put ourselves in a spot where now we've created that situation of same base to some power to some power. What has to be true about those sum powers? Those sum powers have to be equal. Okay, so this, whoops, screwed it up. Subtract the 2x from both sides. And again, it kind of finishes nicely here, x equals 2. There we go. So, and again, you could just offhandedly check. These ones I'm not going to say, hey, you got to check, just because we don't necessarily create that extraneous solution, which you'll see coming up here. But exponential equations, kind of just you solve, they are what they are. Usually 64 squared, you could check it, and then 16 to the 3rd power, are those the same things? Sure, they should check out. Okay, so just connecting it to the homework here, you're going to see a couple, your first 2, just like that. So go back, rewatch the example there if you need to for your first 2 homework problems. All right, next situation. Something like this. We just kind of talked about one. I'm actually going to show 2 different ways here. You could change your change your form. Actually, a 3rd way. So just to kind of review what we talked about on that first slide there. I could just change form if I want. And some of us might say, well, that's the easiest. Now you got to be decent at changing forms. How does this work? Log base 6 of 27 equals x. And I double check it. Okay, 6 to the x power equals 27. Yeah, I basically changed forms. So now you're in a spot here of, oh, I can do that. We talked about change of base formula. Log of 27 right, obviously at this point we don't have a way to evaluate that on our calculator, but I can use my change of base formula from the last section and go log of 27 over the log of 6. We'll get basically what x equals. So that, in the end, almost, it might be the simplest way to do it. I don't know. You got to be decent at changing your form. There's still other options here, okay? That's kind of like a new operation, right? We can add, as long as we add things to both sides, right? I'm just kind of reviewing here stuff you learned a long time ago. You can add the same thing to both sides, multiply both sides. You can square root both sides. You can, whatever, you know, there's lots of different things you could square both sides of the equation and not change the value. We can log both sides of an equation and not change the value. So taking a look here, if I take the log, I'm just gonna, and I'm gonna pick a log that I can use. So I'm gonna use the common log. Log of 6x equals log of 27. You say, well, why would I ever do that? I hate logs. I don't know what they are. Why would I take the log of both sides? So now going back, well, here's the idea that I can get this out of this unknown out of the exponent, right? That was one of those, another one of those properties from last lesson, that if you're taking the log of something and there's an exponent, we can bring that down in front. So by taking the log of both sides, that's allowing me now to bring that exponent down and kind of get it all on the same level. X times the log of 6 equals the log of 27. And remember, don't forget, don't get caught up in all this log stuff. That these are just numbers. Log of 6, log of 27. Okay, how am I going to get this away from this multiply times x? I'm going to divide both sides by log of 6. Log of 6. This would cancel. X is by itself. X equals log of 27 over the log of 6. And look at that. Log of 27 over the log of 6. Cool. So this is kind of like an alternate, just another option as far as solving. Take the log of both sides, almost like a 2b or well, we'll call it kind of a third option here. We can be strategic with this log right here. I picked 10 because it was going to be, I can use my calculator in the end, you know. But if I'm taking the log of both sides, so I'm going to kind of do this one again, but I'm going to use a different base. What if we took the log base 6 of both sides, log base 6 of both sides? Why would I do that? I can't type that into my calculator, is maybe what you're saying, maybe not. But remember those inverse properties. So again, we keep going back to properties that we've talked about this chapter. A log base 6 of a power base 6. How did this work? It was like the easiest homework problems that we did. It was just cross, 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 cross. And then we got basically x equals, okay, right? It was just whatever was left, basically. X equals log base 6 of 27. And now you're essentially, this is almost like a hybrid method, where if you weren't great at changing forms, you kind of like taking the log of both sides. You get the change of base formula here. So how would I solve this? Use your change of base formula. So the log of 27, right? Just take the log of the big number, like a common log, over the log of the base, of the original base. So in the end, whatever method you go, I wanted you to see that not every example is going to be 6 minutes or whatever, but just give you some options as far as how you go about doing this. In the end, you always end up doing the same calculation, right? So I'm 27 log divided by 6 log. I'm getting about 1 point. I think in the homework I have you go, what did I say, 3 places. Just, we talked about that in a previous one, that the further you can go out, the more accurate you're going to be. So I'll just write it right here as a kind of a last one, 1.839. All right. This one's relatively easy to check. You go 1.6 to the 1.839 power. You should be getting close. Remember, it's not going to be exactly, but it'll be close enough to, I think, feel comfortable with. So taking a log of both sides. This really isn't any different, taking the log of both sides. I just wanted you to see one. Was maybe a little bit work to do beforehand, right? Basically, the first thing we did here was just log of both sides, whatever you kind of decided to go with. And I wanted you to see one with an E base. So I'm just kind of just get in here and get it going. I'm subtracting 8 from both sides. Okay. leaving us 6, e to the 0.25 x equals 12. Still get rid of the 6, right? It's not attached for life. Divide by 6, divide by 6, e to the 0.25x equals 2. So this is a good spot, I think, to be. We've gotten rid of just some of the extra numbers. We combined basically these 8s and 6s here. This is one, and I'm just going to show the one method here, but because this base is specifically e, I mean, I could take the log, just the log base 10 of both sides and totally be fine, just like we talked about. I think this is another one that if I take I'm just going to write on the second line here, the natural log, why would I do that, of both sides equals the natural log of 2. Remember, what's going on here? I mean, you can write this base in here for problem-solving purposes. It's an E base, right? So it's, you essentially get that same boom, 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 boom. Now here it's just, that is what it is. But we're basically at whatever's left here, 0.25x. It's those inverse properties. 0.25x equals the natural log of 2. Now don't evaluate this here yet. Let's just get everything together. How could I get rid of this 0.25 times x? It's up to you. Some people say I'm going to divide by 4, or I'm sorry, multiply by 4, right? 4 times 0.25 is 1, or I think most of us just see this as, let's just divide by 0.25. That's how you're going to get rid of that and that. You're going to have the x by itself. So the actual calculation, I'm not going to rewrite it. You can see it here. The natural, that's an ln, the natural log of 2. So I can use my calculator. The natural log of 2, which is some decimal number, divide that by 0.25 or multiply by 4. You should be getting about 2.773. If I round to the 3 places there, and here's 1,000. Again, relatively checkable. Plugging it in, boom, boom, boom. You're going to end up just, do we get close to 20? Sure, it's close enough. So those are that's really the 3, not even 3, really 2 types of equations you're going to see here. So after those first 2, the next 4 all involve, however you want to do it. Taking the log of both sides. You can see some E bases here, so some different things to kind of work with there. Directions, solve, round to 3 decimal place. So those are all doable. I think we can handle those. We'll just scroll ahead here for the next one. So the other half of the lesson is essentially just, okay, solving log equations. All right, so let's do it. So how do I know that it's a log equation? You're going to see the word log, okay? And it kind of starts the same way as the last one. I don't have an example 0 again, but log base 2 of something is equal to the log base 2 of something. The only way that this can be true is if this something is the same as this something. So, of course, this would have to equal 7. That's kind of the theory behind this here. But, yeah, so let's jump in. This one, I think, has 3 distinct types of problems or that I'm going to ask you to kind of understand. So I think it starts extremely easy as far as making sure you got the same base, log base 7 of, again, it's just something, we're just calling this something, log base 7 of something, okay? The only way that this can be a true statement is if this something is the same thing as this something. So you end up with, the only work that I actually need to do is set this something equal to this something still. The work that I'm showing here is what I'm expecting that I'm going to see from you. I'll add 16 to both sides. Okay, 6x equals x plus 15, subtract an x, 5x equals 15, divide by 5 to get x equals 3. I do want to check these ones, and I'll show you kind of what I'm looking for. So when I plug it in, log base, I mean, it's really just making sure that that something is the same thing. So 6 times 3 is 18, 18 minus 6 is 2. Okay, and then the opposite side, I'm getting 3 minus 1, which is 2. So it checks out. We'll see. So this one does check out. You could very easily, though, I'm trying to think, how could I do this? Let's say I solve an equation. Where it turned out, I just want you to see what would kind of prove something to be a not true statement. So log base 7 of, let's say I plug this back in, 3 goes in here, and I get -5, and then log base 7 of, this goes in here, -5. And I'm thinking, hey, this isn't bad, I can do this. It's the same thing on both sides, checks out, but it doesn't, okay? That's kind of the telltale sign, either one, that if I'm taking the log of whatever and getting a negative number, or the log of a negative number, it doesn't exist. Remember, this is like asking 7 to what power gives you -5? I don't know. I don't think we can do that. And remember, our graphs, I know I'm asking you to remember going back a little ways, but these graphs all did stuff like this, a log graph. There were no, I can't get negative outputs. I can get negative outputs, but my x's don't go on this side of the equation here, so, or of the y-axis. So that's kind of what we're looking for. That would be a telltale sign of there's a no solution, or a solution is extraneous. So we'll at least see one as we get into the next 2 examples. That's all we got left. We got 2 examples. So go back, rewatch this one. Hopefully you don't have to watch a ton there, but that's gonna really just, I've got one set up like that for the first one, 7. Okay, 8 and 9 will be like the next one that we look at here. So just kind of previewing it. And I think it's one that after a little bit of work, a little bit of understanding of the logs here, which I think we're hopefully all relatively comfortable with, it turns into another actually pretty, I hesitate to say, use that word, easier type of solve. So what's the difference between this and the previous one? This is kind of what you're looking for. I got logs on both sides, log base 7, log base 7. So that's one type of problem. You've got a log on opposite sides of an equal sign. Another type would be, okay, I've just got a single log on one side. Okay, so I can't just set 2 equal to this because there's no log over here. Okay, but if it's kind of a big phrase here, exponentiate both sides. That's a fancy way of saying change form. What does that mean? Well, this is going back to the first thing we talked about with logarithms. What's the base? 5, go from log form to exponent form. 5 to the second power equals whatever this thing is. We're not used to having like expressions there, but this thing, whether it was just a number or whatever it is, 5 to the second power equals that. So just being able to change forms, we can end up with 25 equals 3x minus 8, and we're saying, hey, I can do that. Okay, let's add in, just add an 8 to both sides. 33 equals 3x, divide by 3, x equals 11. So same thing as before, we do have to check. I know we're still only getting one solution. Like, of course it's going to work, but it is extremely possible that it's really, is this going to be a positive or a negative number when I plug this back in? And sometimes it could end up being negative because we squared stuff and maybe got rid of something that was negative. So log base 5, here's just a real quick check. 5, you can go in right away. 3 times 11, 33 minus 8 is positive 25. And that's kind of what I'm looking for. And I can see here 5 to the second power is 25. Yeah, we're good. So it checks out. It's not a super detailed check, but you're really looking for what is the sign. Is this positive or negative right here? Okay. Last one. Holy cow, look at that. Maybe shortest video ever. This last one's a little bit longer, a little more detailed. So just before we get too far ahead, right, that was that one that we just did. You're going to use that for 8 and 9, that method there. And then 10, 11, 12, it's kind of this last example. So just distinguishing between the 3, just so you can kind of see what makes these 3 different, right? This one just had a single log on one side. This one had logs on opposite sides, same base. Here I've got the same base, log base 10. It's nice, it's a common log, but they're on the same side. And moving one to the other side, and you say, why can't we do it like the first one's not going to help? Let's just say I did that. Like I brought this over to the other side. So if you're doing notes, don't write this here, but let's just subtract a log of 5x from both sides. Well, what does that do for us? It keeps log of x minus 1 on this side. Now I've subtracted this, so it's negative log of 5x. And then this plus 2 is separate, right? It was just already over there. So it's still not the same. I can't just go, oh, x minus 1 equals 5x. Well, that's only true if this plus 2 is not hanging out here. So I got to be a little bit careful there as far as I can't just bring this over. Plus, what's going on with this negative here? We've never talked about really that. And so I need a different strategy than what we did on that first one, where there was logs on both sides. They were both positive, and then there was nothing else hanging out here. So, new strategy. It doesn't really help to rewrite, because how do I do this with on the same sides? I don't know what this is. Basically, our first move is going back to last section and condense this left side. Okay, so go back and rewatch. It was the last thing. It was no, second to last. We did change of base on the last example, or the last notes. But right before that, we were working on condensing logs, going from multiple logs and putting them together in a single. Okay, so how does this work? We're going from 2 logs down to 1. What's my base? It's 10. I don't have to write it. I'm not going to. But what was the connection? When I see addition, I'm adding 2 things. What do I need to do with this and this? When I see addition and I want to condense it, I need to multiply, right? That was this addition goes with multiplication, subtraction, and division went together. So this turns into the log of 5x times x minus 1. So I can condense it, put it all together in a single log, and then we're equal to 2. So I think that does help. We lose a log. It's a little bit cleaner. It's shorter. Now you're still sitting here like, whoa, what's going on? I still don't really get it. Because, I mean, you didn't multiply this. So we can multiply it now. We can do it in a second step, or like in a third step. Basically, I guess this would be our first step. But why not? Let's just go ahead and multiply this out right away. Distribute it. So the log of 5x squared minus 5x equals 2. But now we're basically right where we were on the previous one. Log of log base 5 of this thing right here is equal to 2. This actually ends up being the same number, coincidentally. But now we're at a spot where let's rewrite. Let's change forms. I said change forms on the last one, but rewrite it. What's my base here? If you want to put a parenthesis around this to kind of distinguish it, that this is all grouped together. 10, right? That's my base. 10 to the second power equals 5x squared minus 5x. We go from that rewrite, now the log's out of the problem. Started with 2, shrunk it, condensed it down to 1. When I'm down to 1, that's when I can do my rewrite. So this is 100 here. How do we solve this? This is going to go back even first semester. How do we solve something like this with a squared in it like that? First, let's get this over to the other side. So that's 100, so I'm just going to jump here. 5x squared minus 5x. I subtract this from both sides, so it's minus 100. Oh no! What are we going to do? This would, I mean, you can quadratic formula at this point. I'm personally not going to do that. I don't want to have to touch my calculator or anything like that. The first thing I recognize is that, hey, these are all divisible by 5. Let's shrink these numbers a little bit. So factor out of 5. So now I'm talking x squared minus x minus 20 is equal to 0. And I'm, you know me, I'm always going to look to factor. So I think this is factorable. I'm looking for 2 numbers that multiply to negative 20 that add up to negative 1. Okay. Not bad, right? 5 and 4, negative 5 plus 4, sure. I'm just going to bring this all up here. So I'm sitting with 0 equals, that 5 has been factored out. It's kind of just along for the ride. X minus 5, x plus 4. So that's that's the factored form there. Those aren't my answers, but I think, hopefully, we've done so much of this year. It's nice to see an old school one. What's going to make each of these 0, basically? So x equals 5. If I plug in a 5 here and multiply all this stuff out, added, we're going to get 0. And if I plug in a negative 4, I'm also going to get equal to 0. So those are my apparent solutions. In this particular one, it's going to work out that same way. Don't just cross off the negative one. I've seen them both work. I've seen them both not work. I've seen the positive work, the negative not the positive. So check them both. really it's just that, and this one's kind of different too, so just, I'm going to clear this off here. Just on the check so you can see what's going on here. It's kind of like that first one where it's, if I start with the 5, which I think is going to end up working for us, we end up with, let's see, go back to the original though, 5 times 5 is 25, so log of 25, here's my check. Log of 25, so I plugged in the 5, did the multiplication, plus the log of, let's see, 5 minus 1 is 4, equals 2. So right now it's like, is this true? I don't know. Like, I don't really know if this is true right here. The big thing is they're both positive. Positive 25, positive 4. Now, if I want to know so at least in that regard, I'm feeling pretty good about like our answer. If I want to know if 5 was right, or what if I made a mistake and it was like 6 or something like that, you got to do this condense with the numbers in. So that same kind of condense log of, so go down to a single, and what did we do with these a second ago? We multiplied this times this, so this times this, the log of 100 equals 2, and then I think hopefully you can kind of, yeah, okay, log of 10, or 10 to the second power equals 100. Yeah, that one checks out. I like it. So 5 is good. Here's how I know 4 is not good. So just before you, like I said, before you just, oh, it's negative, so I know it's not going to work. Here's how it's going to look. I'm plugging the negative into check. Log of 5 times negative 4 is negative 20. And then plus log of negative 4 minus 1 is negative 5, equal to 2. Here's why it shows up. So like right now, this is dead in the water, because of what we talked about earlier. The log of negative 20, what are you talking about? That's not a thing. 10 to some power giving you negative 20, that can't happen. So this one, just as of right now, is dead. So I say, nope, this doesn't work. I'm taking it out of my solution set. 5 is my only solution. Here's where you got to be careful, because if I were to condense this, and here's why negative 4 shows up, if I were to condense this, just like we did here, what do I do with these two numbers? You multiply them, right? So now all of a sudden this becomes log of 100 equals 2, and negative times a negative, and then you're thinking, hey, log of, base 10 of 100 equals 2, 10 to the second power equals 100, yeah, it checks out. So that's where you really have to recognize, like right away, that, oh, it's dead, it's over. I'm taking the log of a negative number, can't happen, okay? So I know there's a lot kind of there. Hopefully you watch the whole video and you follow, not just look at the final answer, because that's going to be a little bit tough going back. I kind of jumped around a little bit. So that process of kind of that, you're going to have to multiply it. I think a lot of them are set up where they're going to be a quadratic finish here. Like these are pretty similar, where you're going to have, you can see some x squareds going on there. This right side number, you can see 2, 2, and 3. It's got to kind of stay small in some regard. It doesn't have to, but just to make the problems work out. So 10, 11, 12, that using that process. So it's very straightforward as far as the notes following the homework. Everyone's doing a great job as far as showing the work, and make sure you're checking these ones. I did ask you to check. You can see it right here. I'll say it again. Check your solutions, round to 3 decimal places if necessary. They're not always going to work out that way. Like this first one, it'll be like a whole number. And just if you're printing at home, my fault. I posted it with like a blank third page there. I know you can just re-stick it in the printer, but maybe go to print, do print pages 1 and 2, and whatever. So just giving you the heads up on that. So there's the lesson, 6.6. There's the chapter, really. So we'll come back. We'll see. Maybe we'll do a 6.6, 6.7 quiz, or a shorter thing. The Google Forms one worked okay. I'm still trying to compile the stuff, the results. So we'll see what we do just moving forward. But just for right now, this is all you're worried about, is getting this one done. Kept it under, well, way under 45, under 35 minutes. So have a great weekend. We'll reconnect next week. Either kind of wrapping up 6 as like a shorter quiz in the back half, or just kind of moving on to the next stuff. So that's all I got for you.